In this video I'll introduce Grad-Strovanov solvers. So in previous videos we've looked at deriving the Grad-Strovanov equation and then finding analytic solutions. Unfortunately most of the time there are no analytic solutions, and so we need to use a numerical method to find an approximate solution. And there are at least two different ways these are used. Partly is to interpret experiments, and partly is as a theoretical tool for designing experiments or for understanding the basic physics. And so in this video I'll try and introduce what some of these applications are, and then the different types of codes that have been developed and used to solve the Grad-Strovanov equation. So the two main applications, I say, are first is interpreting experiments, and the second is a theoretical tool. And these can be answered as a forward problem and an inverse problem. So in the first case we have an experiment. We measure some things in the experiment, like the magnetic field at various points around the machine, or we might measure the total current in the plasma, or we might have measurements of the temperature and density at some points in the plasma by, say, Thomson scattering, for example. And from this data we want to reconstruct what the magnetic equilibrium looks like. And so this is calculating the pressure profiles and the poloidal current profiles from experimental data. So the quantities that the code is trying to calculate is the poloidal flux psi, which is a function of r and z, and then the profiles of pressure p, and then f, which is just r times toroidal field. So f is just r times b phi, which also is a flux function. And so these aren't known, but we can find a best fit to experimental data. And typically this is done by assuming some kind of a polynomial expansion for these profiles, and then these are changed to find a best fit to the experimental data. So the other type is the theoretical studies. In this case we know we can specify what pressure and F are, and then from these we want to calculate what the solution looks like. In this case this is in some ways a simpler problem, because we can have complete control over what the P and the F profiles are. And so the problem is just a matter of calculating the potential, so the poloidal flux psi. So typically this forward problem might be a part of what the inverse problem requires. So one of the steps is to take a P and an F and calculate a psi, and then in the inverse problem that psi is compared to the data that you find, and then the profiles need to be adjusted and so on around the loop. Some codes you may come across which do these. There are a few for interpreting experiments. The most widely used is EFIT. So EFIT is an example. There's Clished as well as used at Aztecs, but EFIT is very widely used. For theoretical studies there are lots of different codes for designing tokamaks and interpreting, so performing theoretical studies. Some examples are TEQ, so tokamak equilibrium. There's also Corsica. It's quite a widely used one for things like designing ITER. TES, tokamak equilibrium solver, I believe it was a Korean development. There's things like SCENE, and there's Helena, it's another, also quite widely used. So there are many others of these. Okay, so these are the basic applications, so experiments and theoretical studies. Now I want to look at a bit more detail how this code works. So I'll start with the simpler problem, which is the forward problem. So specifying P and F and calculating psi. Okay, so the basic problem here is that we have a nonlinear partial differential equation to solve. So the Grad-Strovanov equation you can divide up into two steps. So if you start with essentially a guess for what psi looks like, you can use this psi to calculate the current function, which we're going to call capital F, which is also a function of r and z. And this is just the right-hand side of the Grad-Strovanov equation. So we have P prime, which is dP by d psi. And then we have F prime. F prime just means dF by d psi. And so these are functions of psi, and so these are specified. And these are some inputs. So initially you guess this, what this looks like. This allows you to calculate this f, and then from there you can solve the left-hand side of the Grashvanov equation. And this is an elliptic equation for psi. So psi is a function of r and z, and this is an elliptic equation, kind of like a Laplacian. And so we can invert this using fairly standard techniques, but it requires a boundary condition. So we have a two-dimensional elliptic problem solved, so it's in R and in Z. So that typically means we need boundaries on both radial boundaries in R and Z boundaries at the ends. And so in practice we're solving an equation in some domain. We have specified boundaries everywhere, and then if we know f, we can calculate psi, and then this gives us a better estimate for psi, and that goes around this loop. And this loop is called a Picard iteration. That's the basic way we solve this nonlinear problem. This solve here is a linear inverse problem, but we can, all the nonlinear part is in this calculating capital F. And so we essentially choose psi, calculate f, solve to find psi again, and put that new estimate of psi into the loop, and just keep going until psi is not changing anymore, and then eventually finish once psi stops changing. And then we have, at the end, we have psi, r, and z, which once it's converged. I guess this is the Picard iteration scheme, which is used for all these solvers. There are alternatives, but that's the most robust generally. So in order to solve this elliptic equation, we need a boundary. And so now we can talk about boundary conditions. So there are two types of boundaries which are used, and so two types of code which are used. So the first is fixed boundary, and the second is a free boundary. So in a fixed boundary code, we're specifying that there's a shape on the outer edge of the plasma. So we might say that we want the plasma to be this shape. It's typically more a D shape than a circle. And so on this surface, the surface has some kind of normal vector, so right angles. This is the normal vector out of here. And we specify that B dot n is 0, so the magnetic field is tangent to this here. And so that effectively means that psi equals constant. So it doesn't matter what it is, because the gradient of psi is always used. So this could be 0 or could be 1. Just choose some fixed value, and then psi is constant all along this surface. And then we're solving inside this region here, and so psi ends up being kind of something like this, perhaps. So you end up solving flux surfaces inside the boundary. So typical shapes that are used are this kind of parameterization. So you have the major radius, which is going out this way. This is major radius, and this is height, z. So R0 is a kind of value in here. So this is the R0. Then we have a minor radius. So it's major radius, minor radius. So it's cos theta plus delta times sine theta, where delta here is the triangularity. So it's what results in this D shape. So think about triangularity as, if I draw on this, so here we have the midplane, like this. Here we have the maximum and the minimum here. See the top and the bottom. The triangularity is essentially the ratio of this distance here to this shorter distance here. So if I label this, this side is distance A. Oh, not A. A is a bad one. So I label this distance here C. C. This one D. So this triangularity is C over D. So that measures how triangular the plasma looks. A is the minor radius. And then theta is the poloidal angle around here. So if triangularity is 0, obviously then it's just a circle. And then the Z is a bit simpler. So this has kappa, which is an ellipticity, times the minor radius times sine theta. So kappa is called ellipticity. So if kappa is 1, then this is a circle. If kappa and delta, so delta 0, kappa 1 makes a circle. Ellipticity measures how stretched the plasma is. So if I draw again, CD, what can I use? E and F, for example. So ellipticity is the ratio of E plus F. So it's essentially the height of the plasma divided by the width. So the width of the plasma here and the height. So sometimes people use elongation, which is just ellipticity minus 1. So if elongation is 0, then kappa is 1, and it's a circle. So some advantages to this kind of solver. The first is that because you're specifying the shape of the outer edge, you can typically use a flux-aligned coordinate system. So you make your coordinates aligned to these surfaces, and then as you solve the plasma solution, you can change your coordinate system, and this allows quite accurate solutions. The downside is that typically you can't include an X point in these grids. And so you can only solve for the inside the plasma edge, and not outside. So in order to solve outside the plasma, and in order to design an experiment where you don't know what the shape of the plasma is at the start, then you need a free boundary. And so this is the second type, which is somewhat more difficult. So here we specify P and psi. P of psi and F of psi are also specified. But we don't specify the plasma shape. Instead, what's specified is essentially have a like this. So you have usually a square domain. It doesn't have to be. And we have R on this way and Z. And what we're specifying now is the location of the coils. So we say you have a set of coils, so you might have coils around here. So it's really for designing a plasma, designing experiments. You can choose where the coils are, you can choose what the pressures and so on you can achieve are, and you can essentially solve for what the plasma solution looks like. So you can get, say, the surfaces of the flux like this. You might have psi surfaces that look a bit like this. So solving for psi on RZ. Typically this is just a Cartesian, cylindrical grid, so it's in RZ and then constant in phi. So phi is going around like this, but everything is constant. And the way these often work is you might have some shape of plasma that you would like, and so the currents in the coils are under a control system. You have a feedback control which chooses the currents in the coils to make the plasma as close as possible to the shape that you want. But the shape you want may not be possible with these coils, and so you just get a best match, and then you can change the location of the coils or change the plasma shape that you want. And so this is really kind of a way of designing what experiments and what control systems are needed. But it's a much more complicated problem to solve because it doesn't necessarily have any solution. So you might solve this, and the Picard iteration will either just lead to no solution or oscillating solutions, and yeah, can be much more difficult to converge. And so in this case, what's done is the walls here, so the outer edges of the domain, essentially we don't want to have any boundary here, because either there's a metal wall, in which case we can try and model that, but the more common one is that we model this as just a vacuum, so this should behave as if it's not there, so it's a free boundary. Because it essentially extrapolates what the field looks like, and it's not constraining the field inside. So the magnetic field inside is constrained using these coils. And so, as part of the elliptic solve, calculating these boundary values can be one of the most computationally expensive parts. And there are a couple of techniques for doing that, which I'll go through in a later video. I guess the advantage of these is you can, in principle, have any shape of plasma you like. The feedback is slightly more difficult, and control of the plasma shape is more difficult. But you can include X points or snowflakes or very complicated geometries, whereas the fixed boundary solvers are typically restricted to only inside the core plasma. And so what's sometimes done is a combination of these. So you might have a core like fixed boundary solver which solves in this region here, and the free boundary solver which solves for the rest. And so things like Corsica have both kinds of solvers, and combine them both to get high accuracy in the core, combined with a flexible field geometry outside the plasma core. So say some typical ones are Corsica, TES, and then in a couple of videos time I'll show you how to use one which is free, called FreeGS, which is simple because it's written in Python. It's not necessarily the fastest, but it's easy enough to understand how it works. Okay, finally now I want to very quickly talk about inverse solvers and what they might measure in experiments. So how do these work? So if you have an experimental setup here, so we have some kind of plasma inside. So what we know from the experiment is you have the coils outside. So these are the PF coils. Might have a solenoid down the middle. And if the solenoid isn't long enough, there might be some flux outside that, so that might influence the plasma shape. So the solenoid here. Obviously, we have the toroidal field coils around the outside, but the point is we know what these coil currents are. So what we know, so the coil currents, we might have so Monov coils. So these are a kind of coil designed to measure the magnetic field. So we might have coils which are situated kind of outside the plasma. Might have a set of coils, which again might be a number of them down through the center column as well. What is these are just outside the plasma. These are Monov coils. We might have diagnostics which measure typically the midplane, so we might have some kind of profile measurements. So this might give us, say, Thomson. So this gives us some density or temperature measurements. And there can be more sophisticated diagnostics, so MSE, for example. I'll draw this in here. This might give us a measure. So motional Stark effect. So MSE, motional Stark effect, measures the pitch of the field lines. And so combining all these together, the job of an inverse code is to find the best solution. And so it has to find psi as a function of r and z, and also the pressure profiles, so P of psi and F of psi. So the most simple version just uses the currents in the coils and the magnetics. So this is the Murnov coils, this is the magnetics. And there's a diametric, basically a loop around the entire plasma, which measures the plasma current. So we can measure the currents, the magnetic fields, and this gives us a way of finding fits. Let's say this is typically using some kind of polynomial fits. So you have some kind of polynomials for P and F, and then it's a nonlinear least squares fitting problem. So this can be reasonably fast. In fact, some codes have been written to work in real time for control or for operating diagnostics. There's then a slower process if you have things like Thomson scattering or motional Stark effect, and this is typically done post-processing. And there's a refined version called kinetic EFIT, which is when you have EFIT but with these additional constraints. And this EFIT is usually one of the most fundamental parts of the analysis chain. So every time a shot is done on a tokamak, there's a whole load of diagnostics which measure hundreds of data signals, and in order to interpret them, we need to know where in the plasma is the diagnostic looking, where is the measurement coming from. So it might be a probe signal, it might be say a radio wave which is reflecting off a surface in the plasma. And in order to interpret this data, we need to know what the plasma looks like, what's the magnetic field. And so EFIT or some reconstruction is usually one of the first steps in a chain of analysis which happens after every shot. And so this is really kind of a fundamental tool for experimental analysis.